and they find it very interesting. So the topic today that I would like to discuss is more about cyber-physical microgrids. So this is what I started doing during my PhD, but then after my PhD, I focused more on some specific topics, as in how cybersecurity can be important. And then what is the meaning of cyber-physical systems for powertronics or anything else? So let's investigate them one by one. So a bit about myself. I was born in Sambalpur, that's in Orissa, the state Orissa. And then I did my bachelor's in UC Burla, that's also in Orissa. That's one of the quite reputed and one of the oldest universities in Orissa. Then I went on to do my PhD in the year 2015. So I actually started with master's, but then I converted to PhD in IIT Delhi. My supervisor there was Professor Sukumar Mishra. Then following my PhD, I did my postdoc in NUS Singapore, where my mentor was Professor Jimmy Peng. So I did a postdoc stay in NUS Singapore for a year. And then I moved to Aalborg University as a postdoc. And here my mentor would be Professor Fred Blopia. I'm quite sure a lot of people know him already. And then quite recently, I got promoted to the position of assistant professor. So this has been my academic research map, places I've been going through. And then my research areas would be microgrids on stability, control, and design, cyber-physical powertronic systems, and reliability and resiliency of microgrids. And today I'll be specifically talking about cybersecurity. So more about the university. So we are located in Denmark, and if you look at the map, it's actually the Kingdom of Denmark, where you have Faroe Islands, Denmark itself, and also Greenland. So that's the Kingdom of Denmark. And right now, Aalborg University has 3 campuses, one in Aalborg, Copenhagen, and Osbjerg. This has been inaugurated in 1974, and these are the students and number of faculties right now. So we are located in Aalborg, and it's a beautiful campus. A lot of well prestigious rankings. Up recently, we stand at number 3 in the world for electrical and electronic engineering. That is from the Times global rankings, and also the best global universities rankings. Aalborg University stands as the best engineering university and number 4 in the world. So more about the department. This is the Department of Energy. Right now we had some recent updates. We had some modifications, and we had a change in the structure of all the sub departments, you can say. So this is powertronic systems, but now this has been also moved to packaging, control, reliability, and other things. So we have different sections here. But a brief overview of what we are doing: we are also working on reliability on the device level, efficiency improvement for the powertronic converters. Then you have also for, you can say, powertronic based power systems. Could be PV systems, microgrids, e-mobility, wind power systems. So these are all research programs that we have. For power systems, we have modern power transmission systems, energy harvesting, integrated thermal design, and also some other technologies. So these are some of the facts and figures right now for our department. We have somewhere around 40 plus faculty members, 100 plus PhD students, 30 plus RA and postdocs, and around 30 visiting scholars and students. So this is also another opportunity that you can prosper as well. If you would like to visit our campus, if you would like to do some work in our labs, you can also visit our campus for 3 to 6 months, and that should be doable from our end. So yeah, So when I say this topic, so these could be some of the thoughts that are running in your mind. So does this presentation cover resiliency of field devices in microgrids? Does this technology suggest changes in hardware prototyping or topology? That is for the powertronics. So do you need to go for beamforming or any other prototyping technologies? So do you as an attendee need to attend the basics of IT security methods? So I should break that thought, and I would say that you don't need to know any of this. So follow it just from a control theory perspective, and I think you will be able to gather a lot of opinion on this topic. So then we begin talking about reliability versus resiliency, and so I think these two words are very commonly used, but also misused when we are defining both these things. So that is why I have created a comparative chart of where reliability stands and where resiliency stands. So reliability is more about monitoring some high probability and low impact events for, let's say, power systems or microgrids. But resiliency is all about low probability and high impact events. So yeah, we are looking at two different set of events here. Resiliency can be adaptive, ongoing, short, and long term, but reliability is usually static. It's a static analysis. It can be for maybe 10 years, 20 years or so, and that's how we calculate the damage of many of the system, or let's say the components. It depends. So reliability only evaluates the power system states, that is the up and down state, but resiliency also calculates or accounts the transition time between these states. So when the system goes down, what is the time to bring the system to up state, and which means the reliability index in that case. So when you say that the system is down, then your system is below the defined reliability criteria. And if it's up, then it's above that. Customer interruption time is concerned for reliability, but here customer interruption time and also the infrastructure recovery time is concerned. So like I said, the transition time is actually a big criteria here to define resiliency. So the lesser the recovery time or the lesser the transition time, you can say that the system is quite resilient to any high impact events. So this is just one of the definitions that I would like to say. And then the factors affecting resiliency. There are many emergency management guidelines from NERC, EPRI, and DOE. These are all the research institutes and the funding agencies in the US who have defined what are the likely high impact, low frequency events. Could be extreme weather, natural disasters, and also some man-made anomalies. Could be in the physical layer, could be in the cyber layer, or could be in both cyber physical layer. So 60% of these events have caused power outages. 90% of them have actually occurred in the distribution systems. So when we talk about the man-made outages, and these are some natural outages, you can say, but some of the man-made anomalies, the vulnerabilities keep arising. The dynamic outage measures have also been defined, but because we are getting more and more connected due to the cyber layer, decentralization is usually recommended in this case. So what are the challenges behind resiliency in powertronic systems? You can see that increasing powertronic units are actually demanding a faster response from some of the sources. And with the grid modernization, where we have a lot of information and communication technologies, modern sensing equipments, we are undergoing a massive change in how we see the system. So of course, it has its own benefits, but it also brings with it some flaws, which has exposed the modern power systems to cyber attacks. So when I say the modern power systems, you have to picture a system, power system with dominated with powertronic generators. In that case, the inertia, it's a low inertia system. The generation, the nature of generation, the dynamics of generation has completely changed as opposed to what we see for our Indian grid today. So from the power outage event reports in electric grid, it can be concluded that control layer for powertronic systems can be most vulnerable to cyber attacks. So where can these cyber attacks be located? Where are they most vulnerable? So we have concluded that control layer can be most vulnerable. And all the controllers, so let's say your MPPT or anything that you're using, power controller, synchronization controller, frequency response, frequency regulation, you assume that they are operating with unbiased measurements or inputs. So this is one of the biggest assumptions, and we would like to investigate if they are really biased or unbiased using some cybersecurity mechanisms. So this is how I would define the grid-tied microgrids, where you can say that there are many microgrids connected to distributed energy sources. Could be battery, PV, electric vehicles, also consumer loads. So there are many ways in which they can be connected to the grid. And you also have communication, which is used for condition monitoring, control, fault diagnosis, a lot of things, and how they are transferring all the information into different nodes. So you can say that this is one supervisory controller for microgrid I, and another supervisory controller for microgrid 3, another supervisory controller for microgrid 4. So this is just to take care of the power management within the microgrid and also the grid. And if we have to exchange power between two microgrids, there is a network microgrid energy management that can be interfaced into the system. But because there are a lot of vulnerable components right now in this modern power systems, could be communication access points, or could be even the circuit breaker switches, the problem of reliability and resiliency arises. How reliable and how resilient is our system to these kind of disturbances? So some of the grid supportive services from grid-tied microgrids could be frequency regulation, virtual inertial support, frequency response, and reactive power support. Yes, and then we have islanded microgrids, which is autonomous. They're operating among each other. They're not sharing power back into the grid. So these are some of the common objectives for AC microgrids. Could be frequency restoration, proportional active power sharing, voltage restoration. How do you decide to share the reactive power? It's pretty much up to you or up to the system, to be precise. And then you have DC microgrids where you're trying to also share the current and restore the voltages. So this is one of the common structures where you have a DC microgrid and you have an AC microgrid. So you have the local controller, and there is the cyber graph, which is the communication topology of how each converter is connected, or the measurements, how they are being shared between many converters. So that is why I call it as the cyber graph, because it denotes the flow of information between two nodes. Okay, and based on that, these are some of the local information that we intend to share to the cyber graph. And we also get some of the neighboring information or information from the remote sources in this way. So we use the locally measured information and also the communicated information into the secondary controller to come up with some frequency and voltage references in this case. And the converter is supposed to operate for these frequencies, and similarly for DC, except for the fact that we do not have a frequency here, we only have the voltage reference. The local information measured, or even the control inputs can be used for the secondary controller. So let's start with the definition of cyber attacks throughout the presentation, and this is how I would go ahead with the definition right now for this case study. So it does not mean that cyber attacks can be, are entitled to this definition. It can be anything, but this is how I would like to define cyber attacks based on the amount of presentation and amount of work that I have done. So it is said to be conducted by a third party in an illegitimate manner by injecting false data or denying actual data from single or multiple sensors, communication links, actuators in the control systems to disorient the system objective. So whatever is the system objective that I have defined in the previous slides, if you are able to disorient that by injecting false data or denying actual data from single or multiple sensors or communication links, then it becomes a problem, and that's a cyber attack for now. And it's a very simple definition that I provided. So they can be very simple to detect, or they can be very smart, which cannot be detected by some of the existing bad data detection schemes. Now, if you look at this is like a false data injection where you are injecting a false data. Okay, and so this is the data acquisition and calibration unit that is there in front of the controller. And you have a sensor measurement. So if you inject a false data into this, I'm quite sure that if you have employed an observer inside the controller, it will be able to find out which sensor is actually, faulty. But if you do this, let's say if these sensors are of equal, of the same nature, and if you inject a false data somehow that it makes sense to actually add them up and it sums up to be 0. So this is basically zero dynamic if you inject this into the controller. So in a way, you are adding them up and that sums up to be equal to 0. So this is smart. So if you have a controller, if you have an observer here in the controller, it will not be able to detect because it's a zero dynamics attack. Okay. Then man in the middle, where you are injecting a control input into the communicated information between two controllers in this case. And when you do so, let's say you are trying to talk to controller 2 and you say that, hey, I will be there, but the cyber attacker actually injects another information. Hey, I will be there in 5 minutes. So controller 2 actually receives the wrong information in that case. This is how the man in the middle attack goes on. And then this is basically denial of service. So it rejects any information from controller 1. So it does not allow controller 1 to talk to controller 2. So this is by actually injecting random packets into the communication layer. So the problem statement from here could be that if you have many layers, which is the physical layer, the cyber layer, and also the control layer, the physical layer has a, let's say this is the converter. And there are many security mechanisms, which is the hardwiring of the sensors to the PCB, beamforming, which makes it pretty much impossible to go ahead with any cybersecurity attacks. And then in the cyber layer, it could be the information exchange security mechanisms where you have the encryption, right? You can have many firewalls. And that depends on the application where you would like to implant a cyber link. So let's just assume that this is quite safe. But the biggest problem is, even if these two layers are safe, you are injecting the measurements from the physical and the cyber layer into the controller. But for the controller, there is only one security mechanism, and that is the operating system. So for your case, could be Windows firmware security, which is regularly updated. And that is the only update that you receive from anyone. And they can be easily hacked. And based on the previous translating some of the attacks in the power grid, you can see that the operating security can be penetrated or can be broken by some of the Trojan or some of the phishing attacks. and which means that if you receive an email and I somehow implant a Trojan into this and you click on that link, then I will be remotely accessing your system. So people can be remotely accessing this platform, and they will be able to change some of the monitoring, data acquisition, and also some of the user-defined reference commands. So I can give you an example. Let's say you have given a command to operate this power tonic converter at 50 Hertz. So you obviously need to give a command on the frequency reference to 50 Hertz. But if I am remotely accessing this platform, I can change this reference value to from 50 to 55 Hertz. And because you are in an interconnected system, that can create synchronization issues and you will be tripped out of the system. So the assumption is the control environment is operating with unbiased measurements. And the problems in powertronics could be it can lead to immediate shutdown due to over voltage, over current, protection measures under cyber attacks. Because if you inject a false data into the frequency or voltage or anywhere, you will see immediate ramping up because you are operating with high switching frequency. So any false data is going to ask you to ramp up the generation, which is not really possible because this was not even there in the first place. So some of the reports across the globe, electric aircrafts, ships could be the key targets with critical priority on security. These are autonomous systems, and these are, well, you can say medium voltage microgrids. And there have been some reports earlier. You can also find a report which is very popular that was in the Jeep Cherokee. And so you can imagine this for electric vehicles as well, which has 4 drives. And somehow they were able to change the torque distribution among 4 drives. And that led to many problems. I think how they got into the Jeep Cherokee was through the entertainment system. So when you are in your car, you also try to play some music by connecting your phone, connecting your phone to the entertainment system through Bluetooth. And that can be a very easy access into the car control system. So that was exploited in that case. So do you have any questions until now? Or should I go ahead? Okay. I believe there are no questions. So some of the state of the art and some of the research questions that you can take from this presentation, and you can work on this. So all the cybersecurity solutions have been covered for slower operations in power systems that could be from 5 to 15 minutes. But these solutions cannot be accommodated in, even if it's 1 minute, it cannot be accommodated in powertronic systems because any false data or any denial of service or denial of signals for powertronic systems for even milliseconds could be a big problem because the control system is expecting signals in real time in maybe few milliseconds or a few microseconds, so to say. So that could be harmful. So how can you design a faster solution for powertronic systems? Resiliency capability of powertronic systems have never been used. So what is the resiliency capability of powertronic systems? So let's say if this is the reference at which it is operating, let's say this is the frequency, and you injected a critical disturbance here. So how quickly can the powertronic converter come back to the reference? And that is the resiliency capability in this case. So in terms of cybersecurity perspective, what is the critical time within which the detection of cyber attack has to be attained in view of stability considerations? So what should be the minimum time, or what should be the critical time within which you detect the cyber attack such that the stability is attained at all times? Can it be 1 second? Can it be 1 microsecond, millisecond? You need to find that out using theoretical studies. Now, recovery to the pre-attack point, the feasibility studies. So what are the conditions under which recovery back to the pre-attack set point cannot be attained. So that is in connection with this question, because if it becomes, well, steady state unstable, then you may never reach the reference point. And you also need to do some feasibility studies when it will never reach the reference point. So that is another point. Now, again, this AI, that is the artificial intelligence for data authentication. So up to what limit can AI be trusted for authentication data used for the training itself? Because if there could be any adversarial points in the data used for training, then AI is also going to, or your neural network is also going to maloperate in that case. So what are you really going to do? So how, up to what limit can you trust this neural network? So coordination strategy, these are the two common coordination strategies here. One is the centralized philosophy and one is the distributed philosophy. So in this case, you can see that the one to the left is a centralized mechanism and the one to the right is a distributed mechanism. So all the nodes here are a converter, okay, and they are sending their information to the central controller. And here, all the nodes are just sharing the information between only the neighbors. Okay, so that's the communication philosophy. So the dotted lines here are just flow of information, and that's not flow of power. Okay, this is only the cyber layer, the communication layer. It has nothing to do with the physical layer. Now, the distributed control, highly reliable, scalable, and economic. And this is more secure because even if you have, let's say, a link failure here between 4 and 3, you can still get the information of 4 by following the return path, okay, in 3. But you cannot do so here because if you lose the cyber link information from central controller to 4, then you can never have information from how 4 is operating. So you only have 3, 2, and 1 for the central controller to operate. So I think centralized controller could be easy, but they're highly prone to cyber attacks because if a cyber attacker pins down one of these, then your system is already lost. Okay, so let's now talk about cyber physical microgrid. And this is just how I have projected a simple system of DC microgrids where you have multiple DC-DC converters connected to a common bus through tie lines, and you have some loads. It could be resistive, could be constant power, depends where you are. And then you have a controller here where you have the primary control and you have the secondary control. I think these are all basics of the control strategy. Where primary control, if you have read about the low frequency control as well. You have the primary control, which is the group control, and you select the group coefficients for this. So the group variables are voltage and current in this case. And because of the group, you will never be operating around at the reference. So that is why you go for the secondary controller, where you try to restore the voltage. And also you can have a current sharing between all the converters. So that's the purpose of secondary controller for DC microgrid. So why do we call it cyber physical? Because it's a confluence of the physical and the cyber layer as well, so that we can get a very, improvement in performance. So this is how I would define it as cyber physical, because if the cyber layer goes unstable, the physical layer is also going to see some instability. And if the physical layer goes unstable, the exchange of information in the cyber layer is actually going to add more unstable modes. So this is how they are deeply integrated into each other. So you can see that when the secondary controller is activated, they are actually equally sharing the current. And whenever there is a load change, all the converters are mandated to share the current equally. Okay, and for the PCC voltage, when the reference was somewhere around 48 volts, they are doing so. Okay, and this is without any cyber attacks. But when we actually do the cyber attack, you can see that you still anyway follow the same objectives that I defined, and this can be done by following a very smart trajectory of attacks. So how can these smart attacks actually manipulate this? So as you can see that these bolts are representing the cyber attack. Yeah, so they can be injected into the sensors, which is the current sensor, voltage sensor, controller, or communication. So let's assume that all of this information can be, it's not an assumption, but this can actually be true because they are anyway reported to the controller. So you can actually manipulate the controller or the sensor or the locally measured or communicated values from the controller itself. And you can see that when I inject a smart attack into the controller, you somehow see a load change. But this was actually not a load change. This was actually a smart attack on the currents. And also for the voltages, for the average voltages, you can see that they anyway converge back to the reference. So now you would think, how is this possible? That because there was no load change here, but when we inject a smart attack into some of the converters, it actually looks like a load change. Okay, so you as a system operator would think that, well, this is not a problem. This is just a system, some system disturbance. So everything is working fine. But because you have already injected the cyber attack elements into many sectors here, okay, and you can remotely change it, edit it. So what you can do is after staying stealth for some time, so after staying quiet for some time, you can just unfairly increase the attack elements and it will go into this, look like something like this. So the voltages ramp up in no time. So I think in a matter of 0.2 to 0.3 seconds, you have already lost all the converters because this is the over voltage threshold of the system. So in a way, you can expect the circuit breakers to be operating at this stage. And when they saw all the converters ramping up here, they disconnected all of them. All right. A similar case also for the voltage as well. When we injected smart attack on the voltage counterparts in DC microgrids, you can see that there is a transient, but it anyway comes back to the average voltage reference, that is 315 in this case. So yeah, no more changes voltages. The current is also being equally shared. Current sharing error is 0. So as a system operator, you would think everything is fine, but after staying quiet for some time, they followed another cyber attack, which is an unfair increase in the attack elements. And you can see that within no time, I mean, I don't think it's even 0.1 seconds, you have already lost 2 of their converters. Okay, and that is going to create a big problem. So it can be a full system blackout or a partial system blackout. So you need to be alert against these cyber attacks. Yeah, detection of stealth attacks is what I can say is these are some of the common control philosophies that is already devised in many papers. So I try to understand the control philosophy here and try to came up with some of the existing signals and not design another observer on top. And when I see that they are losing the consensibility, so the general idea is if there are the communicated measurements and the local measurements here, and they are following or they are in consensus here, then they should also be in consensus somewhere over here. They should always be in consensus somewhere over here. And when any of these signals is losing consensibility, you can say that the voltage of that converter is basically attacked. So for current measurements, we have come up with a discordant element, which is this metric. And for the voltage, we have come up with a cooperative vulnerability factor, which is this metric. So what we do is we subtract the communicated measurement with the local measurement. Okay, so we come up with a term like this and a similar term, similar structure. And when it is 0, then we say that, okay, this is not attacked. And when it is more than 0, then we can say that the voltage of this converter is attacked. Similarly for current as well, when it is more than 0, then we can say that the current of that converter is attacked. All right. Now we have a similar case for also for the AC microgrids. Here you can see this is just one of the converter structure across the LCL filter. And there could be n number of converters. So in this case, n equals 4. And you can see that when I injected a smart attack on the frequency as well, they incur a change in the transient, but they anyway converge back to the frequency reference here, that is 50 Hertz. And even although these cyber attack elements are present, and when there is a load change, you can see that they anyway converge back to the frequency reference. And after some time, when you unfairly increase the frequency attack elements, it actually goes outside the range of operation. So this is where your circuit breakers are waiting to operate. And you can see that within no time, 2 of your converters are already lost here, okay, after 3.5 seconds. When we see for the active power sharing as well, even though the attack is there, there is a transient, but they anyway converge back. Okay, and after the unbalanced attack, which is the somehow the worst attack, there's a huge oscillation and the system goes unstable. So in a way, you have already lost your system here, somewhere around here. Then, so after detecting them, we try to come up with a mitigation strategy, that is the event-driven resilient strategy. What you do is you actually reconstruct another signal based on the attack detection criteria. So like I told you, that it should be within a particular boundary. If it is within 0, then it's all right, 0 or a very small value. But if it crosses that value, then what you do is you actually use that attack detection criteria to stay or to force them to stay within the upper and lower threshold. And based on this, if you know that one of the signals which is not attacked, you can get this information from other converters. You just sample and hold. So every time you hit the upper threshold, you create a trigger. Whenever you create a trigger, you sample one of the information here and then hold it until you receive the next trigger. So in this way, you are actually creating a digital replica of this signal, and then you can actually use it or replace this with the attack output. So in a way, the attacker cannot really do anything else with your converter. So we have tested this for different energy management schemes. Could be the generation cost oriented, reliability oriented, and capacity oriented. And we also have copyrighted this to the university. So yeah, mitigation would be the first stage is detection using the proposed detection strategies. And then we can actually come up with some binary signals which can depict that if a particular measurement was attacked or unattacked. So that will be the detection monitors here. You can see that if it is positive, then one of the converters is attacked and the rest are below the region, so they are unattacked. Similarly for this one is a voltage, this one is a current. And from there, we authenticate them. So we come up with some labels. So if this one is attacked, then we can say that you should not trust this. You should put an authentication label of false. And then we go on to this, this stage where we mitigate them. So if you receive any false measurements, okay, then what you do is you try to look for the trustworthy measurements. So the other measurements can be trustworthy. And based on this, you can actually follow the signal reconstruction and come up with a triggered signal in this case. So now you are going to use this signal instead of the attack signal. And that is how you are going to mitigate them. So this is again for AC as well. Like I said, that when you attack the frequency, you can see that the active power references, they should be in consensus, but because they are not in consensus, now they have followed a different path. Okay, so the ones who have followed a different path or who are not following the consensus anymore, they are the ones who are attacked. So in this case, you use these information or the frequency of this converter to be false, and then use the rest of the signals to reconstruct another signal, and instead use this frequency as the frequency reference or the frequency measured frequency for the attack converters. So the signal reconstruction can be used in both DQ and ABC frames for AC. And the threshold is very important to predicate the resolution of output signal. So if the threshold is less, then the output signal will be more, the resolution will be high. So an overview of what we have done, event-driven resilient strategy. So we have done the stability analysis, feasibility for all cyber attacks, sensitivity analysis for, let's say we can also have noise and other things, performance for all degrees and sophistication of attacks. Computation, it's very simple. You do not have to employ another observer or anything. You just have to use the same thing, same controller. Performance under worst case cyber attacks and extension to all energy management schemes. That is also done. And we do not need any data. We do not need any historic data from the system. So we do not use any artificial neural network or anything like that. So some of the future outlooks from here that you can also incorporate into your studies, or yeah, we can also work together on these things. So where do you feel the security management needs to be? Is it control? Is it hardware? Or is it cyber layer? Which one is better? Could it be artificial intelligence or could it be physics informed? What can be a good tool for resiliency? And you have to also note or consider the factor that you are in a system where you have, let's say, the data can also be manipulated. So you should be very careful about using AI here. Preliminaries of protection schemes. So yeah, you also need to consider different protection schemes and how they can be differentiated with the man-made anomalies. Threat assessment of powertronic systems. So you need to consider and understand where are the threats located. So some of the important references, some of the papers that I have published in this connection. So this is all about cyber attack detection. So 2 of them are in transactions on powertronics and 1 is in transactions on industrial electronics. And when we talk about the mitigation, there are 4 main articles, which is mostly all of them are in transaction on powertronics. There is 1 on transactions on cybernetics. And some of the fundamentals on cybersecurity in powertronic systems can be referred from this paper. It's an open access paper, actually. Cybersecurity and control of grid-tied powertronic converters, challenges and vulnerabilities, where we translate the concepts in powertronic-based power systems. We assess the vulnerabilities and also the control challenges for a large, I would say, subset of powertronic-based systems that could be DFIG, HVDC, STATCOM, DSTATCOM, and also microgrids. So yes, I think that will be the end of my presentation. So if you have any questions, I would love to answer them for you.
Hello.
Hello. Yes.
Yeah. From where do we get the local signal to subtract from communicated signal? From where are we going to get the local signal in a vast system, big system?
Yeah. Local signal is something that you measure locally. Let's say the sensors. Okay. So imagine you have a grid connected PV system. Okay. So you have the VPCC point, that is the voltage across the PCC point, current across the PCC point. So you do not need communication to actually measure these signals because these are very close to the converter itself. So in that case, you can just locally measure them.
Yeah.
But if you need to have, let's say, measurements from a remote grid connected PV system, then you cannot just take the measurement from the sensor itself because it will be very lossy, right? And anyway, the sensor measurements give you a signal of, or return a signal within plus minus 5 volts. So if you are going to extend this over a lossy line, then that is, so in that case, we need communication.
No, that's right. But communicated signal is received
Yes.
And we need to compare it with the local signal for generating the error and the correction action, right?
Yes. Yes.
We need to compare two. For example, in an interconnected grid, you will have a local a load dispatch center where all the signals would be communicated. There they will be receiving the signal. This is just for an example. They will be receiving the signals through communication. Now, if I want to know whether it is a cyber attack or not, how do we get the local signal from the substation to compare with it? Because substations are located
Well,
far
that's
at a far remote place. Yeah.
yeah. I think that's a very different case study that you are saying for the dispatch center. I think most of them will be communicated in that case.
Yes.
So you have to figure out how do you
Another
want to
strategy.
compare it. You know.
There some other methodologies to be found out because there this local signal comparison will not work, isn't it? Is it?
Yeah, but that's actually I have not done that studies.
I understand. I understand.
Understand
Yeah,
what you mean.
it is a different domain. I got it. I got it. Yeah.
Yeah, I think that's a good question, but that's something that I have not considered. But what you can do is there could be two local or two communicated signals in that case. And I think you can just compare them based on your objective. So let's say if you are trying to minimize the cost, the generation cost, or something like that, in that case, or I don't know what your objective
No,
is. So you need
stability,
to understand
stability. Yeah.
how can a cyber attacker, disorient your objective.
Yeah. Okay. Fine. Yeah. Thank you. Thank you.
Thank you. Thank you.
Sir, this mitigations method depends on the type of communication used.
Not really. No, not on the type of communication. It can be any communication topology. It's just something that we do in the controller itself. So yes, the type of communication will imply different communication delays, and we have a limit within which we can achieve the solution. But yes, I think for distributed control system, the limit is somewhere around nowadays. I can even achieve these results up to 1 second. So even if you have a delay of 1 second, we can still get the results. Okay, so I think with different communication protocols, you will have different delays, so that might affect the performance. But the nature of communication is not going to be a big task.
Okay, sir. Sir, what about the if some islanded detection algorithm is implemented? Is there any chances of conflict between these things?
I actually could not follow your question. Can you go again?
See, actually in microgrid concept, there are chances of islanding. So islanding detection algorithms are generally used for the detecting the stability of grid.
Yes.
So can you there may be some conflict between these, or they are totally isolated, like
No, I mean
islanding detection techniques?
yeah, I mean it can be for the grid. I mean islanded grids as well. And if you are targeting that a cyber attacker can target islanding detection, then yes, it's possible. It is completely possible. You need to figure out, but I think that will be more. The research has to be done more in the communication layer. In that case, we are also trying to work more on how to differentiate between faults and cyber attacks. In fact, you can read them. You can find them in these papers. I have not presented in this slides, but I think you will find the results in the papers how we have differentiated between grid faults and cyber attacks. Yes.
Sir, one of the question in chat box that asks, what about consumer and security?
Yeah, consumer is. I think that's not really a big target for the cyber attacker. I mean, you have to think it like this. What will the cyber attacker get if they, let's say, attack a consumer set point? Yes, they can get a lot if they are going to attack on a transmission line set point, or if they can take out the sources one by one, then the generators will be overloaded in that case. But from a consumer set point, I don't think it is a very big, could be somewhere, let's say, privacy and other things, but not really a big impact on the system level. I think it's all about philosophy, so to say. I can say that cyber attacks can be possible at different set points, but you need to imagine a scenario where it will have the most. Actually, you can just unmute yourself and ask. I think it will be better.
Yes, it's better. Madam, please unmute yourself and ask.
Okay, thank you for giving me the opportunity. Sir, my question was like if a person or a cyber attacker, they may hack because now it is in grid, so they are the user, and again their data is going to get feedback to the grid. So it's a closed loop. So they can attack from any point, like if they are attacking from the consumer point, or they are polluting the total system, like they are injecting more reactive power or something like that. So in that context, I was asking, so can we put any security over there also?
No, I think it can be a bit costly if you install cybersecurity solutions across the consumer end. But I would still say I would like to focus more on some cybersecurity solutions in the generation end itself, and try to analyze, let's say, some impedance scanning methods and other things, so that we can say that from the consumer end, the impedance has higher frequency or something like that, or let's say if you have more reactive power injection, then it is in a way polluting the grid, or the power quality measures are being deviated. So that can be one of the methods. But if you are planning to propose a solution or pitch it to any industry or something like that, because you have to understand where is going to be the loss, because cyber attack is not just about polluting the grid, but it is also about incurring a loss. So who are the payers here? Who are the players? And that is always going to be some distribution system company or TSO or many other things, and they are paying for all this. So in that case, if they can attack one of the consumer set points to have some power quality, or to distract from some power quality index, then they need to check with this from the generation end, not in the consumer end, because they cannot install any cybersecurity. That will be very costly. I think they will never be convinced with this. I hope I was able to answer.
Okay, sir. Thank you, sir.
Yes, thank you for the question. Yes. Okay, I think.
Is there any questions from participants, or we'll conclude it? Yes, Ketu, sir.
Yeah, sir, pertaining to resiliency, how much time do you have to decide, that is make decision, because power electronics converters operate very fast and are operating in the high frequency range. So how much time do you really have for your system to detect and act upon the attack? Yeah.
Good question. I think I can demonstrate this by a video. Maybe you should like this.
Sure.
It depends on a lot of factors, actually. It depends on, how big your system is. If we are looking at a large transmission system with different capacity of generators and other things. But I'll just give you a simple example of a very small system with two converters. They are connected to each other through tie lines, and there is a load in between. Okay, so imagine this: two DC sources connected to each other through tie lines, and there's a load in between. and they are asked to share the load equally. So these are two controlled voltage sources. Okay, and this is from our experimental setup. So yeah, do you see the video now?
Yes.
Yes.
Okay, perfect. So can you picture this for me? Two controlled DC voltage sources. Okay, they are connected to each other. So let's say they are at two different ends and they are connected to each other through a tie line resistance, and there's a load in between them. Okay, and they are asked to share the load equally.
I can see the waveforms. System representation is not there. On the left side, you are talking about the dialog boxes.
No, I'm just trying to picture it in your head. I have not
Fine.
started.
Yeah. Okay, got it.
So this is the current of both the sources. Okay, you can see now I started firing the converters, so they are sharing the load equally. I think I will do a auto scale operation to show you that it works perfectly. Works good, right?
Maintaining within a range, right? Yeah.
Then I will conduct a decrease in load. It works perfect again. Increase in load works perfect again. And now if I am the attacker, I can see this, but you from your system, if as a system operator cannot see this. So you have something like this, but the attacker has one extra access point. So I inject a value of 1 into one of the converter's current. So you can see that it still shares the current. And this one could have been 100, could have been 50.
Okay.
And it's a very small system. So if I inject a fairly high value, then your system is gone. But this was just an attempt to show you that what can these cyber attacks do. You can see that they're sharing equally again. So if you are the system operator, you would also think that, well, everything looks fine. I don't think there's a problem. Then I start the resilient controller. And you can see that they converge back to the same value they're operating at. And when I increase the value to 100, you can see that the system is unaffected because I have already replaced the attack signal with the reconstructed signal. So in this case, I would say that there could be many scenarios which can actually create a problem. So let me show you another one. This is another video. Okay. And this is where I will conduct or inject a value into one of the communicated lines. Okay. And this is where you see that when you inject a cyber attack, how quickly the system comes back. They're not sharing equally because there are different groups. I don't know where the groups are. Yeah, 0.9 and 0.3.
Yeah.
This is an increase in load. The resilient controller is started, so they come back. So even if there's an attack, you can see it
within very short time.
The voltage as well, it pulls it back. And now I inject a value of 15. It pulls it back again. So it can be, it needs to be very fast, as you can see. And if you go slow about it, then you have already lost the system because they keep ramping up. And if they are trying to ramp up, then you have already lost the system. So it needs to be very fast.
Correct. Okay. Thank you.
Yes. Okay. So are there any more questions?
Dr. H. Vanilla, your hand is up. Is there a question from your side? sir.
Last question, sir.
Yes, yes.
How not question, but request to share your contact details if it is not there in the presentation. I don't know. Yeah.
Oh, it is there in the presentation.
Fine.
This is my, yeah, I can, yeah, this is my contact details. This is my email address. You can just email me.
Right.
And I can, yeah, I can quickly come back to you. I reply quite quickly. So
Thanks a lot. Yeah.
if you have any concerns, just write to me, and I can discuss more about what we are doing.
Great. Sure. Yeah.
Yes. Thank you so much.
Thanks a lot. Yeah.
So we are concluding the session here. Thank you so much, Shubham.